will be recorded. Okay, so this is a time that I'm going to do the organic chemistry week 13, the recap, and this time I'm going to focus on SN1 versus SN2 reaction, and also E2 versus E1. You might even think about why you don't say that SN1 versus SN2. Actually, I'm saying that SN2 versus SN1 because SN2 is a little bit more easier to understand than SN1, but this is both possible scenarios, and then organic chemist has to look at their product to actually justify their mechanism for this reaction is SN2, which is a bimolecular reaction, or SN1, which is a unimolecular reaction. E1, E2 is an elimination reaction, whether it's involved with a two molecule at the same time, that's a E2, or E1 is just a unimolecular reaction. What that means is unimolecular. They actually go through the two-stage reaction. First, they develop this carbocation activated molecule, and then there is another reaction following this. So before go to the recapping those topics, I am going to solve you quickly these two exercise problems. And this is an exercise. One problem is what they call the electrophilic addition. The other one is a carbocation arrangement. And so let me just do the quick way for you to see how I solve this problem. Okay, so I see the double bond here. Okay, I see the double bond here, and I can see that HCl means a proton source, and they can be easily dissociate. And then they say using the proper arrow, I explained it a few times in my previous YouTube video, it is a movement of the electrons. So this pi bonding here, those bonding will try to form the bonding with the H plus, so that by doing so, there are two carbons are involved here, connected through the pi. One of the carbon will be will make a bond formation with hydrogen. The other one will develop the positive charge. So therefore, you can see there are two scenarios. One is hydrogen is connected to here, and then develop the positive charge on this side. And the other one is actually hydrogen is connected to here. Right? There used to be hydrogen already, and develop the positive charges on this side. Right? So here I am now shifting my focus on to the carbocations that you see here. And then what you see here is I'm going to highlight the carbons. So this is a carbocation. There's a carbon here. There's a carbon here. There's a carbon here. Do you see the three carbons? So this is what we call the tertiary carbocation that has the high stability among these alkyl carbons. And this is a carbon here now. You have only carbon and carbon here. And the third one is on hydrogen. So that doesn't much of a help. So this is a case. We are asking you whether carbocation-wise, which one they would like to prefer to form. Tertiary carbon, right? The one that where this side is developed, the C plus here, and that's exactly what you see here. But this is a very unstable compound, C plus. This is what they call the transient and excited state molecule, which is because of when you see this carbocation is sp2 hybrid orbital, and then it's only the 6 electrons, so it's a very, in a way, very unhappy. It's just we are talking about something that is, which one is relatively more stable, given that this is a transient structure that they need to be fixed by having the bond formation. Okay, so this is the carbocation. Because of the insufficient electrons for this carbocation, they need to accept and form the bond and sharing the two electrons formed an extra bond there. That's just the nature that trying to satisfy the octet rule. And if you're looking at what has happened after this dissociation, you're left with a chlorine. And this is a chlorine that would like to form the bonding, right? So they go here, and they form the bonding. And so this is a newly formed chlorine that has been docked to the one that is, essentially this is a one, what used to be the 3 tertiary carbocation position that is being preferred to develop upon the protonation and then here. So this is, you can say, protonation, and then CCl bond formation. You can think about their stages. And the key idea is which one is more stable? Tertiary carbocation is more stable. Okay, so the second problem is a little bit more difficult, and this problem is actually very favorite topic for many organic chemistry types of question when you take a exam in, let's say, any GRE exam or MCAT exam for grad school application or medical school application. Carbocation arrangement, in other words, the most common one is called the hydride shift. And also, sometimes if hydride shift is not available, then methyl shift. Okay? They are trying to move those bonds around to actually enhance the stability of carbocations. So this problem, if you're looking at, if you don't understand, if you do not consider this, you might get it into the wrong problem, and that's a tricky part of this. So this is the same problem. If you see here, okay, HCl. Okay, I can see that. There will be a H plus and Cl minus. They can dissociate, and I can say, well, double bond will be trying to form the bonding here. So first step is protonation. And then you can do the same thing. Okay, so there are 2 carbons involved in this, and do they want to form the bond on this side and forming the positive charges here? And in this case, what do you see? You see the tertiary carbons, right? This carbon, there are 2 carbons surrounding this. Or the other case is, if you do this, having this one connected to, okay, hydrogen can be put it in here, and there will be a carbocation can form the other side. In this case, this is a primary, right? This is a primary carbocation. So this is not good, right? So therefore, I want to go back to my choice. Okay, hydrogen. Oh, sorry. Let me do undo. So hydrogen will form by protonation, and the carbocation will be formed here. And if you just follow the same logic that is in the previous problem, then and you will see, okay, so then probably I can see that chlorine form the bonding here, right? And if you just simply do that, and then this must be the original molecule, and then the chlorine should be form the bonding with that carbon here, right? So that's the picture. But do you see that? The answer is no. And so there is some other process once they develop the carbocation. Before they do this, they are going to undergo. So yeah, I can keep this one probably. So no, they want to do what is called the carbocation rearrangement. What that means is, if you see secondary carbocation, and if you can make it into the tertiary carbocation, that's the way they will do, either by essentially hydride shift or methyl shift. Okay, so that's the idea that you should implement it here. And that's the second step. And what you see here now, I'm going to use a different symbols. So I know that this is where the carbocation should be developed first. That's for sure. But now you're seeing this neighboring carbon. This carbon has this attachment, right? This is a methyl attachment, methyl attachment. So by doing so, they are going to go through the carbocation rearrangement, because this is a secondary carbocation. And then let me get rid of this for just simplify this. And then this CH3 methyl group, and those bonding electrons in methyl will be connected to form the bonding with the carbocation carbons. And by doing so, the second step, what you see here is, okay, so protonation have this, and there are 3 methyl groups. I know that. And then this one will form this, what they call the 1,2 methyl shift. And by doing so, you are developing, if you look at that, I just draw the same one. And here I'm just highlighting this new bonding in blue, which is now they are connecting through here, right? Do you see that the change before and after? Because this is a carbocation, and that bonding with this CH3, now I'm coloring blue now, and that one is now formed the bonding here. As a consequence, by shifting this methyl, you are developing the positive charges on the other side. And so that's the rearrangement, which is the second step. Okay, so more details on here, which is a redundant to the one that in before. And then what you have at the lingering outside. This is what's the ion that is lingering outside, right? So this is a chlorine minus as this lone pair electron. They want to fix the problem of carbocation by forming the bonding here, right? So then what do you see here is, this is a molecule. I am going to kind of the color in a way, orange way. There is a carbon, 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 carbon. So it looks like this, right? And you guys can see I'm going to color in the same way. That's the carbon skeleton, carbon-carbon hydrocarbon skeleton. And then the new bonding is being formed by this chlorine ion. And so that's the new bonding that is being formed. And so that's why you are not expecting to have, so because of the carbocation rearrangement that is shown up here, you have a new location of attachment that is shown up, and that's the second problem set of the problem. Okay, so I just want to tell you a little bit about this. This is your slide from the Dr. Ma's class, and then they call the 1,2 hydride shift, and they call the 1,2 methyl shift. And this is when you think about that and the hydride shift, and this whole thing is moved to the neighboring, and the methyl shift is the whole thing is moved to the neighboring carbocations, right? So carbocations, and they form this. And in reality, this is actually the formal charges is a negative and negative here. That's why we don't say hydrogen shift. Hydrogen shift. Instead, we call hydride shift, because this is a negative ions. In the same thing that people should call it methyl shift is not maybe the correct one. They should say methide shift, right? But what has happened in the organic chemistry community, they don't call it hydrogen shift. They always call the hydride shift. And as far as the methyl is concerned, for the same reason, the methide shift is a term that you use, but also they just simply call methyl shift. This is too much information, so they just mix those two, both are accepted term, And as far as the hydrogen is concerned, the hydride is the term. And I would like to ask one more point here. If this compound has an option to do hydride shift versus methyl shift, which one will be the nature will do the shifting? They have to shift one to essentially typically change the carbocation from secondary to tertiary carbocation in order to do that. Who's a winner? This is a winner, okay? Because of the hydride is a much swift, light atoms that they can easily move around. So they are the one is swift motions, and they just neutralize a carbocation, and then the other carbon that is used to be the hydrogen is connected to develop the former charges, the carbocation. So actually, my example will have that one. This is a little difficult concept, but I think that you'll see my example to the following. So this is a new part that I didn't record it in my previous one. And let's talk about that SN2 versus SN1. And then here the SN2 versus SN1. And I'm picking up the example by Dr. Ma that has been shown up here. So here's an example that this is for the sake of the problem, say, I am going to assume that SN2 reaction is occurring now. So given that, we are just assuming that SN2 reaction is occurring. And then my task is pretty simple now, because Na plus and OH minus is going to happen here. And then this OH minus is a nucleophile. Okay, so they have this nucleophile. Sometimes they put a little dots because of the lone pair electrons are there, and that's the one that is essentially humming for. It's like a missile. They are looking for anything that is positive here. And if you're looking at the molecule here, this is the electronegative chlorine. So, okay, that's not what I want. This is the one that is chlorine is more electronegative, so they are pulling the electron. This carbon here is developed partial positive charges, so therefore this lone pair electron is looking for, and they are going to react this molecule on here. The carbon here trying to form the bonding. And this is a one that actually, let me delete this, and I want to show what Dr. Ma has put it on the note. So they're going to form the bonding. And he said that from the top only, and then I'm going to elaborate that onto here. So this notation, so let me draw it one more time. This is what is called the cyclohexane ring. And the cyclohexane ring is sort of, you can think it about as on a plane. The real representation is a chair form, and there is an axial position versus equatorial position, and this is all different concept later on. But in a naive sense, you can think about this one being, so this is probably this chair notation is something that you will do it later in the organic chemistry when you spend taking the 2 semester long class. But in a very naive sense, and this is not a bad idea, think about this is on a piece of paper, okay? And this you have this hexagon molecule on that sort of the plane. It's not exactly on the plane. I will tell you right now because that's not true. But I'm saying here is this is on the plane, and then now you can see this molecule, this notation here, which means a chlorine on the here is essentially moving away from here, right? And the methyl group, CH3 methyl group that you see here, that's the one that is actually sticking out of the plane. Oh, CH3. Okay, so that's the how it looks like. So what about the other ones? I'm going to put a same color here. This means that you have a hydrogen that is actually coming like this, and so does, I guess, you can see that hydrogen, there's a hydrogen that's shown on this notation on the left. Okay, but this is, having said this one, what's going to happen is you have a OH minus ion trying to do the reaction, and this one says SN2. Okay, so it means this molecule here and the OH minus nucleophile, they have to react together at the same time. And so therefore, you have this chlorine on the other side moving away from the kind of the lying down onto the opposite side of this the plane. Right? So if I kind of put a little notation here, this is on here, right? So this is, they are on side, on a kind of on this plane, and then this chlorine is kind of in a way invisible, right? So they are underneath it, and so therefore this one is coming from the top. Okay, and so that the chlorine is on the bottom side. So by doing so, what is your final product is you have this one on the plane, but now the chlorine is gone, and this one is what is on the top. You have an OH minus forming the bond, and naturally the hydrogen on the other side to kind of keep it on the tetrahedral structures, and you will see this compound having a CH3 and an H. Okay, so that's the product of SN2 reactions, which is you have a top only, right? So this is a top only because of the CCl bonding is at the bottom. At the bottom, or you can say the other side of the plane, so that this one is connecting this one this way. Okay, so the whole information is very important because it is saying that it's an SN2. And then I like to elaborate that this one by using this as an opportunity to explain what about if SN1 is the mechanism. Right? You can postulate that mechanism. So this is what organic chemists do when they discover the new reaction. And it's okay, if it is an SN2, then what's the scenario is going to be is, okay, so you have a compound, looks like this, and then you have chlorine, which is at the bottom. I mean, I'm drawing the same problem before. So this is the same compound, but SN1 means you are going to generate the carbocation. Yeah, you're losing the chlorine minus, right? Lost the chlorine minus, and then you are making this carbocations here. And then you are going to have this what is the OH minus ion trying to form the formation of the bond. And so now have a look at this scenario. I would like to I think that in my video I talked about this. This one is essentially form a plane, right? So this whole thing is in the same plane as before, just like the one as I shown above. So let me do the a little bit more consistent. So let me draw the once more. The mechanism wise, I want you to visualize a little plane here, and then this time you are going to have this one lying down on that same plane, and I guess the methyl is sticking out, but now this one is positive here and it's on the plane. Okay, so carbocation, to give you a little short summary, it is an sp2 hybridization, and the formation of the bonding is the trigonal planar structures. I like triangle planar, okay? but you can fancy the name. Trigonal planar structure is the correct one. So what I'm saying here is organic chemist is a very well known to leave this hydrogen out. So hydrogen out, and then these neighboring carbons and carbon, they form this on the plane. And so as I did it before, they are on this plane, right? So this is like on a plane, like this. They are on this plane, and what's going to happen for this OH minus? That essentially it's like a humming missile, right? So this is a nucleophile that onto the carbocation based on this is an SN1 mechanism if it were to, and they can go, and then this nucleophile can go from the top, or they can actually go from the bottom, and both are possible. Okay, so this is a little bit more higher end of comparing this. So you see this. This case is top possible. This is a case where both are possible. For if it is a word to the SN2 mechanism, this is the top is SN2, bottom one is SN1, and you develop carbocation first, and by doing so you will have this notation now. The double bond methyl sticking out, fine. So you can visualize the plane that defined by the cyclohexane ring, and then this methyl is OH is forming the bond from the top. I guess as a consequence, if you want to show hydrogen in the bottom, right? And will be the methyl is from the top. And then this one is this time the hydrogen is going up because hydroxide formed the bonding from the bottom surfaces. Okay, so now what you see here now is let's compare this. So in the SN2 cases, you are forming this complex. So which is the same here, right? But at the same time, in the SN1 mechanism, if they were to, they'll form these mixtures. Right? Sometimes you will see this case. Now let's have a look at it. Do you remember the C plus notation chiral carbon center, which is this one? First thing is sp3 hybrid orbital, and that means a tetrahedral attachment, and then carbon with a tetrahedral attachment is 4 different attachment, has to be all different, right? 4 attachment, alpha, beta, gamma, delta, 4 different attachment. And then we actually, I think that this is one of the Chem 1 problem that you assign. This one is a chiral carbon that can have an optical isomers and so on, right? Remember, this is from the previous one. And now you're looking at this carbon here, and this carbon essentially has this attachment, that attachment, this attachment, that 4 attachment. And the 4 different direction is not the same, right? This one is a carbon with a methyl attached. This one is a carbon with 2 hydrogens attached, and hydrogen and hydroxide. So therefore, this is the chiral carbon here. Okay, so this is a chiral carbon. So I will just put a little star marks here, and that's a chiral carbon. So you are having this. This is one chiral carbons, whereas if you look at here, there is nothing changes here. These are the 2, both are chiral carbon centers, but these are the essentially you're having a pair of optical isomers. Okay, so then what do you call this? This is a, have you heard about racemic mixtures? Okay, so this is a case. You will get this racemic mixtures in when the reaction occurs. Your mixture is a racemic mixtures, whereas if the reaction is occurred, this only one type of optical isomer, right? So that's for the SN2. So now you can see this, the two different scenario. One is an SN2 reaction. You have only one type of optical isomer. When you have a SN1 types of reaction upon the formation of carbocation first, and you will see this one is forming racemic mixtures, or because OH can go from the top or from the bottom at the equal opportunity. So you will have a mixtures of optical isomers, or you will just have a one type of optical isomers. And depending on your outcome, people actually say, well, I find that the mechanism is based on SN1 or SN2. I guess in this case is the justification for this is the chlorine is not so good living group because of the carbocation has to be generated, whereas this one, OH minus is such a strong nucleophile, they're going to just like a push, make a bonding to get rid of the chlorine. So this is almost like a billiard ball colliding onto this side and leaving the another ball to the other, kicking out the other bonds outside. So bimolecular mechanism is most likely because of the strong nuclear filling nature of OH minus ion that's looking for any kinds of source of the partial positive ion right there. Okay. And I will talk to you about this, the second practice problem. This is also from the Dr. Mas one, and this is actually worth for to think about the case. So this is the word to the E2. Okay, and then he said the three products. But okay, so E2 means elimination. Okay, elimination means this compound here, which is a CH3 oxygen, they form the anion and lithium plus. Okay, and the really crucial information is, okay, so I'm telling you this is going to happen by E2 elimination reaction. So then in that case, you are looking for something looks like this, and we call this as a base. Okay, so base is quote unquote base, and so this base is looking for to take hydrogens from this molecule, and here you have a hydrogen here, right? And that's the one that they're trying to take it out, or they can have one hydrogen here, right? And which one will be the most protic? And because of the same logistics before, this is a delta positive here, and so therefore first instinct is not this hydrogen, but that's the hydrogen. They are trying to take it out. Once they do, they have a different way. Okay, so I think that I got that confused now because of this is not the way that the elimination reaction should occur. So elimination reaction E2, you should actually understand that first thing is a base, and you create a double bond. That's the elimination reaction. So therefore, this is actually lone pair electron is going to make a bonding with an hydrogen, and leaving bond to the forming a double bond here, and then this chlorine will be leaving as a chlorine minus. So as a consequence, what's going to happen is I'm going to draw the same structure here. I just showed essentially the carbon skeletons, and then what has happened here is now they formed a double bond here, and then this one, you see the hydrogen used to be there. They're still keeping the hydrogen as they are. So this is a double bond form based on the E2 mechanism. E2 is essentially you have to take the hydrogen. This is a delta positive carbon, and then you can find the neighboring carbon, and the hydrogen that connected to the neighboring carbon, that's the one that they are going to take it, and then for the formation of the new double bond as shown up here. Okay, so that's the new double bond shown up here, and this is a bimolecular mechanism. The mechanism for E1 is a lot more complicated and more things to consider, so I'm going to discuss it the remaining time. I think I'm going a little bit over time, but please stay with me because this is a complicated, but if you're understanding this concept, you are in a good trajectories. Okay, so this is I guess a double bond being formed, and then what are the three products that he mentioned? The other product is so CH3O, they get the hydrogen, so that's the one. They will be like this, and what's going to happen to chlorine? There will be a chlorine minus. Okay, these are the three products, but the more emphasis on these types of organic compound based on the E2 mechanism. This is what you think that is going to happen. If you're looking at the other side here, there is no hydrogen can be lost, so only this side can happen. So that's the only possibilities, and this problem is really simplified because it's assumed that E2 mechanism is what's going to happen. Okay, but now let's change it. What about if E1 is the mechanism? Okay, and then you can predict essentially the products. So I'm going to draw the same chemical structures with the carbon, and then 2-methyl is attached to here. And this time, this one, E1 mechanism means this one just leaving as they are. The chlorine will be lost. Okay, chlorine will be lost as this anion form. And you naturally develop this carbocation. So that's really the heart of the main differences. It's a unimolecular reaction, so you develop this activated carbocation one, and then now you have to look for the source of hydride shift or methyl shift. Okay, so if you look at that, this is wait a minute. This is a secondary carbocation, but now I see this. Okay, I see this methyl. Okay, so I think the methyl shift, just like we have done before. Or second option is, you see the hydrogen here, and then they can work at hydride shift, right? And which one wins? Hydride shift versus methyl shift. And I told you that the hydride shift is the one that, because of the lighter nature, it is a much swift motion, and this will have. So therefore, for this token, and there will be a hydride shift, 1,2 hydride shift. And by doing so, I'm going to draw the same skeleton. This is a trimethyl there. But now this one, and then they have this, and they essentially form the new hydrogen bonding, carbon-hydrogen bonding, and then the carbocation move the position from the being secondary, right, to the tertiary position here. Can you see this carbon with carbon, which is a methyl, CH3, CH3, and the carbon here. So this is now all of a sudden that tertiary carbocation. That's a beautiful thing, because and that's the one that they want to form this structures here. Oh, I should not do that. I just want to get rid of the carbon only, but let's see. Okay, I cannot do that. So I'll just leave things as they are, just like that. And then what's going to happen is now E1 mechanism, now you're looking for something like what is called a base, looking for the H+, right? In here, it is a CHO minus, that's your base, and they're going to take the hydrogen from many different occasions here, right? So one way is this carbocation is there is a 3 neighboring one, and either they can take the hydrogen here, or they can take the hydrogen on this side, and they will love this take the hydrogen from this. So they want to take this one hydrogen, and this one can form the double bond here, right? And then what the final structure looks like, it will be something looks like that, with a double bond with this compound, right? CH3, CH3, and then this trimethyl. And the other one is, if you're looking at this other option, which is taking this one out, right? And so this is a case 1, this is a case 2. That's the number 1, and that's the number 2. And if this is a case, then you will form this compound, that carbon with double bonds here, CH2, and then CH3. So there are 2 different possibilities for E1, and from here we need to have another rule, and the rule says that what is called have you heard about this? I cannot is a Russian name. Is what they call the Zaitsev rule, and which alkane is formed higher yield when you do the E1 reaction. The one with the most substituted alkane is the one they will favor. And so therefore, this one is this product is most, this double bond shown up here has a most kind of attached form, because this one is only 2 main attachment, whereas this one is methyl, and something the carbon here. So this is the final product that you see. So now let's compare this to the one that's showing up here, right? So this is the one that, can you see this? The one that showing up here, this is based on the E2 product, double bond is embedded in the middle, and then this one is actually happen to be the same. So we cannot distinguish those two for whether it's an E1 or the E2, but there's but we can essentially make different kinds of scenarios. Sometimes you will ended up having different products as you go along with this. Okay, so once again, the E1 mechanism is once you develop these carbocations, and then the base is trying to take the hydrogens, and so as a consequence, the double bond is being formed onto the other side. Okay, so this is where the double bond is being formed, and that's the one that I wanted to end this on my session here. Okay, so a little bit rushed to the end, but I hope I have given